All right, so let's kick off with, I think it's Ashima Keshava, who's going to talk about some eye movements and virtual reality stuff. Brilliant. All right, Ashima, do you want to unmute yourself and go for it?
Perfect. Thank you. So I'll share my screen now.
Yes, that would be great. Yeah.
Do you see the panel underneath?
We don't see we just see at the moment, we're just seeing your like web browser.
Perfect. Okay.
So it's not full screen yet.
Yeah.
Okay, now it's full screen, yeah. And we can see the panel, yes.
I'd like to get rid of, okay, perfect. Okay, welcome everyone. Thank you for attending my talk. I'll be talking about preparatory eye movements that reveal prior knowledge and intended interaction in virtual reality. This is a project that I started this year with Nina Gochevsky, Faber Nizami, and my lab supervisor, Peter Koenig at the University of Osnabrück. Okay, so what is the motivation of my study? So in everyday tasks, eye movements have been found to be primarily driven by top-down factors such as task relevance and less by saliency. For example, in the Lang and Hayhoe paper in 2001, they did a sandwich making task with subjects, and subjects fixated on only task relevant objects such as the bread, the jar, the knife that was used to spread the jelly. So they concluded that only task relevant objects are fixated on during a task. Furthermore, eye movements are also used to extract visual information in a goal-oriented way. For example, in the Bellardinelli study from 2015, they studied how subjects would fixate differently when asked to lift an object versus when asked to open the lid of the object. So when the subjects were asked to lift the object, their fixations were more centered towards the center of gravity of the object, so like so. And when asked to open the lid, subjects fixated more towards the location where the action was supposed to happen. So they concluded that fixations are goal-oriented, and these anticipatory fixations also reveal the intended interaction of the subject. And so here we ask how eye movements extract information from unfamiliar objects when prior knowledge is not available to the subject. So this is my experiment design. The experiment takes place in virtual reality. We have a 2x2x2 within subject design with factors task, familiarity, and orientation. In each trial, the subject has to interact with a virtual tool, either by lifting it or using it. Use would be pantomiming the use. I'll show you an example of how this interaction looks like. We have 12 tools in total, 6 of which were familiar and 6 were unfamiliar to the subjects. The handle of the tool was oriented either to the left or the right-hand side, which corresponded to the factor orientation. In total, we measured, we had 144 trials per subject over 6 blocks. The task orientation and the tools were counterbalanced so that we had equal number across participants. We measured 18 participants. I wanted to measure more, but because of Corona, it was not really possible. And we measured these participants in a simulated environment using HTC Vive Pro Eye. And we try to assess the naturalistic gaze behavior using these 3 factors. This is how the VR environment looked like. So this is the HTC Vive setup, where the head-mounted display is set up before the experiment. The interpupillary distance is calibrated to the participant. This is the calibration phase, where subjects are shown 4 dots. And after the calibration is successful, the simulated environment starts. This blue dot is used for validation to check that the calibration error is less than 1 degree. If the calibration error was more, we had to do the calibration again. And now the experiment starts. So this is a virtual hand that was used that was shown to the subjects. This corresponded to the real hand. So this is a use condition where a tool is presented, a beep is given to the subjects, which corresponds to the go cue, and subjects can press the button to get on to the next trial. Here, a spatula is shown. The subject can lift it, go on to the next trial. The same tool in a different orientation. And so on. So these are the 12 different tools that we use. The familiar ones would be, should ideally be familiar to you. These are everyday objects that you might use. And in the unfamiliar tools, for example, this is a lemon zester, which subjects don't really know, are not really familiar with. This is a spoke wrench, which is used for bicycle repair. So if you are a repairman, you would know this tool, but our subjects did not. And this is a daisy cutter, which is used for gardening. All of these tools had predefined regions of interest. So here we had a collider on the effector part of the tool, which was pre-made before the experiment. And here on the right side, we have the handle, the collider over the handle, which is our region of interest for the handle. And a questionnaire was also administered to the subjects after the experiment to assess the familiarity ratings, subject-specific familiarity ratings for each tool. Our hypothesis was in the use condition, more fixations would be on the effector of the tool, while in the lift condition, more fixations would be on the handle of the tool. For the unfamiliar tools, more fixations on the effector, and these would be, and fewer fixations on the familiar tools. And in the use condition with unfamiliar tools, there'll be more fixations on the effector compared to familiar tools. And the orientation of tools would elicit more fixations on the handle for both tasks due to the incongruence of the grasping direction. So this is how we analyzed the data. We studied the fixations made before the go cue, before the beep, and we modeled these fixations as log odds of fixations on the effector compared to the fixations on the handle using a linear mixed effects model. So this is how our model looks like. We have the probability of fixation on the effector divided by probability of fixation on the handle and the log of this. And this was dependent on the task familiarity orientation with random slope and intercept over subject and a random intercept over our items, which is the tool. All our categorical variables were effect coded, so they were not dummy coded as in 0, 1, they were effect coded to minus 0.5 and 0.5. And here we ask, how do familiarity, task, and orientation affect the fixations on the effector? This is the data that we have. So on the y-axis, you have the log odds on the effector. Values above 0 would indicate the odds of fixations on the effector, the odds of fixations of being on the effector, whereas values under 0 would be the odds of more odds of fixations on the handle. In the familiar condition, we see that in the lift task, the fixations are mostly on the handle for both the left and the right orientation. And in the use task, there are more fixations on the effector, but slightly, so the odds are slightly towards the effector, but not as much for when the tool is presented with the handle on the left side. In the unfamiliar condition, there were the fixations were more towards the effector in general. And in the use condition of unfamiliar tools, there were higher odds of fixations on the effector part of the tool for both the left and the right orientation of the tools. This is what our linear mixed effects model revealed. So in the use condition, the odds of fixation on the effector is higher, and this is significant. For unfamiliar tools, the odds of fixations were very much on the effector, and there was no significant effect of orientation when the handle was presented on the left side. In the use condition and the unfamiliar, in the use condition for unfamiliar tools, there are a higher number of fixations on the effector part of the tool, and this was significant as well. For the use condition, when the handle was presented on the left side, there was a marginal effect of the fixations being more towards the handle. For unfamiliar tools presented with the handle on the left side, as well as for use unfamiliar on the left side, the coefficients were not significant. So in conclusion, we can say that preparatory gaze strategies differ for a given task, in this case, use or lift. Unfamiliar tools elicit more fixations as a way of extracting the mechanical properties of the object, because the affordance of the object is not directly known, so it has to be inferred. This strategy is exaggerated when using an unfamiliar tool. And the orientation of unfamiliar tools marginally affects these preparatory gaze, but not significantly. And in conclusion, we can say that eye movements reveal prior knowledge and intended interaction with an object in VR. And with that, thank you for your attention.
All right, thank you, Ashima. Okay, we have a couple of questions just coming in right now, actually, which is cool. So the first question is just a quick one, I think. Were your subjects right-handed?
Yes, we made sure that all our subjects were right-handed, because it wouldn't make sense if the handle orientation was incongruent.
Right. Yeah, that makes sense. So Lewis is asking, so more a suggestion, unless it's a question. Why did you code for left-right relative to the user's orientation and not in terms of handedness congruence?
So it's easier to get right-handed participants for one, so we just had congruent to the handedness basically. So the handle on the right side would be congruent to a right-handed person, and a handle on the left side would be incongruent. Okay. Yeah. Mm-hmm.
I have a couple of sort of more general questions, but do any of the other panelists want to knock in and ask a question actually at this point? If so, just go ahead and unmute yourself. No, not particularly. Okay, so I'll ask some of my more general, naive questions in that case.
Yes, please.
So what I was wondering actually is, in your virtual environment, it's quite relatively simple, right? It's a flat shaded, not many objects. Could it be that the way people handle sort of more realistic environments, which are much sort of busier visually, could be different from what they would be in such a simple environment?
So I am running a follow-up experiment with more textured environment where it's more natural. It looks like you are on a workbench, you're working with a workbench, you have more wooden textures, the tools are much more real looking, and we have the interactions that are used not with the controller of the HTC Vive, but with leap motion. So leap motion would be that you do not have a controller in your hand is rendered naturally in the environment. So even very small finger movements could be rendered in VR. And we want to see now if this heightened immersion can cause either a breakdown of this effect, or how does it affect the results for us.
Okay.
But it's in progress, and hopefully if we don't have another lockdown, we should be able to have some participants.
Yeah. Well, actually, I have a follow-up on that, but since we've got another question from the audience coming in, I think I'll ask that one instead. So, so Lewis asks, could you expand on your experience with eye tracking in VR and how that restricted your potential inferences with regards to this topic of preparatory responses to objects?
So eye tracking in VR is messy, of course. As you saw in the example, there are head movements, so you have to account for differentiated velocities in the eye. We found that using median absolute deviation based fixation detection to be quite useful for us, because the eye movement data is quite noisy to begin with. And that helps us in a data-driven approach to fixation detection. But I'm not sure if it restricted our potential inferences. We do check all of the fixations per trial by hand and see if it makes sense. There is some amount of pre-processing, more than in a particular lab experiment that we have to do for VR eye tracking. But yeah, I hope that answers your question, Lewis.
Okay, that's great. All right, so I think we'll have to call it a day there for this session. Thank you again very much.
Thank you.
That was a great talk and really interesting to see VR being used like this. All right, so next up we have Paul.